Chapter 8, Part 3 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Approaches and Landings, Part 3. Crosswind approach and landing. Many runways or landing areas are such that landings must be made while the wind is blowing across rather than parallel to the landing direction. All pilots should be prepared to cope with these situations when they arise. The same basic principles and factors involved in a normal approach and landing apply to a crosswind approach and landing. Therefore, only the additional procedures required for correcting for wind drift are discussed here. Crosswind landings are a little more difficult to perform than crosswind takeoffs, mainly due to different problems involved in maintaining accurate control of the airplane while its speed is decreasing rather than increasing as on takeoff. There are two usual methods of accomplishing a crosswind approach and landing: the crab method and the wing-low side-slip method. Although the crab method may be easier for the pilot to maintain during final approach, it requires a high degree of judgment and timing in removing the crab immediately prior to touchdown. The wing-low method is recommended in most cases, although a combination of both methods may be used. Crosswind final approach. The crab method is executed by establishing a heading, crab, toward the wind with the wings level so that the airplane's ground track remains aligned with the center line of the runway. See Figure 8-15. This crab angle is maintained until just prior to touchdown, when the longitudinal axis of the plane must be aligned with the runway to avoid sideward contact of the wheels with the runway. If a long final approach is being flown, the pilot may use the crab method until just before the roundout is started, and then smoothly change to the wing-low method for the remainder of the landing. The wing-low side-slip method will compensate for a crosswind from any angle, but more important, it enables the pilot to simultaneously keep the airplane's ground track and longitudinal axis aligned with the runway centerline throughout the final approach, roundout, touchdown, and after landing roll. This prevents the airplane from touching down in a sideward motion and imposing damaging side loads on the landing gear. To use the wing-low method, the pilot aligns the airplane's heading with the center line of the runway, notes the rate and direction of drift, and then promptly applies drift correction by lowering the upwind wing. See Figure 8-16. The amount the wing must be lowered depends on the rate of drift. When the wing is lowered, the airplane will tend to turn in that direction. It is then necessary to simultaneously apply sufficient opposite rudder pressure to prevent the turn and keep the airplane's longitudinal axis aligned with the runway. In other words, the drift is controlled with aileron and the heading with rudder. The airplane will now be side-slipping into the wind just enough that both the resultant flight path and the ground track are aligned with the runway. If the crosswind diminishes, this crosswind correction is reduced accordingly, or the airplane will begin slipping away from the desired approach path. See Figure 8-17. To correct for strong crosswind, the slip into the wind is increased by lowering the upwind wing a considerable amount. As a consequence, this will result in a greater tendency of the airplane to turn. Since turning is not desired, considerable opposite rudder must be applied to keep the airplane's longitudinal axis aligned with the runway. In some airplanes, there may not be sufficient rudder travel available to compensate for the strong turning tendency caused by the steep bank. If the required bank is such that full opposite rudder will not prevent a turn, the wind is too strong to safely land the airplane on that particular runway with those wind conditions. Since the airplane's capability will be exceeded, it is imperative that the landing be made on a more favorable runway, either at that airport or at an alternate airport. Flaps can and should be used during most approaches, since they tend to have a stabilizing effect on the airplane. The degree to which flaps should be extended will vary with the airplane's handling characteristics, as well as the wind velocity. Crosswind roundout, flare. Generally, the roundout can be made like a normal landing approach, but the application of a crosswind correction is continued as necessary to prevent drifting. Since the airspeed decreases as the roundout progresses, the flight controls gradually become less effective. As a result, the crosswind correction being held will become inadequate. When using the wing-low method, it is necessary to gradually increase the deflection of the rudder and ailerons to maintain the proper amount of drift correction. Do not level the wings. Keep the upwind wing down throughout the roundout. If the wings are leveled, the airplane will begin drifting and the touchdown will occur while drifting. Remember, the primary objective is to land the airplane without subjecting it to any side loads that result from touching down while drifting. Crosswind touchdown. If the crab method of drift correction has been used throughout the final approach and roundout, the crab must be removed the instant before touchdown by applying rudder to align the airplane's longitudinal axis with its direction of movement. This requires timely and accurate action. Failure to accomplish this will result in severe side loads being imposed on the landing gear. If the wing-low method is used, the crosswind correction, aileron into the wind and opposite rudder, should be maintained throughout the roundout, and the touchdown made on the upwind main wheel. During gusty or high wind conditions, prompt adjustments must be made in the crosswind correction to assure that the airplane does not drift as the airplane touches down. As the forward momentum decreases after initial contact, the weight of the airplane will cause the downwind main wheel to gradually settle onto the runway. In those airplanes having nose wheel steering interconnected with the rudder, the nose wheel may not be aligned with the runway as the wheels touch down because opposite rudder is being held in the crosswind correction. To prevent swerving in the direction the nose wheel is offset, the corrective rudder pressure must be promptly relaxed just as the nose wheel touches down. Crosswind after landing roll. Particularly during the after landing roll, special attention must be given to maintain directional control by the use of rudder or nose wheel steering, while keeping the upwind wing from rising by the use of aileron. When an airplane is airborne, it moves with the air mass in which it is flying regardless of the airplane's heading and speed. When an airplane is on the ground, it is unable to move with the air mass, crosswind, because of the resistance created by ground friction on the wheels. Characteristically, an airplane has a greater profile or side area behind the main landing gear than forward of it does. With the main wheels acting as a pivot point and the greater surface area exposed to the crosswind behind that pivot point, the airplane will tend to turn or weather vane into the wind. Wind acting on an airplane during crosswind landings is the result of two factors. One is the natural wind, which acts in the direction the air mass is traveling, while the other is induced by the movement of the airplane and acts parallel to the direction of movement. Consequently, a crosswind has a headwind component acting along the airplane's ground track and a crosswind component acting 90 degrees to its track. The resultant or relative wind is somewhere between the two components. As the airplane's forward speed decreases during the after landing roll, the headwind component decreases and the relative wind has more of a crosswind component. The greater the crosswind component, the more difficult it is to prevent weather vaning. Retaining control on the ground is a critical part of the after landing roll because of the weather vaning effect of the wind on the airplane. Additionally, tire side load from runway contact while drifting frequently generates rollovers in tricycle-geared airplanes. The basic factors involved are cornering angle and side load. Cornering angle is the angular difference between the heading of a tire and its path. Whenever a load-bearing tire's path and heading diverge, a side load is created. It is accompanied by tire distortion. Although side load differs in varying tires and air pressures, it is completely independent of speed and through a considerable range is directional proportional to the cornering angle and the weight supported by the tire. As little as 10 degrees of cornering angle will create a side load equal to half the supported weight. After 20 degrees, the side load does not increase with increasing cornering angle. For each high-wing, tricycle-geared airplane, there is a cornering angle at which rollover is inevitable, the rollover axis being the line linking the nose and main wheels. At lesser angles, the rollover may be avoided by use of ailerons, rudder, or steerable nose wheel, but not brakes. While the airplane is decelerating during the after landing roll, more and more aileron is applied to keep the upwind wing from rising. Since the airplane is slowing down, there is less airflow around the ailerons and they become less effective. At the same time, the relative wind is becoming more of a crosswind and exerting a greater lifting force on the upwind wing. When the airplane is coming to a stop, the aileron control must be held fully toward the wind. Maximum safe crosswind velocities. Takeoffs and landings in certain crosswind conditions are inadvisable or even dangerous. See Figure 8-18. If the crosswind is great enough to warrant an extreme drift correction, a hazardous landing condition may result. Therefore, the takeoff and landing capabilities with respect to the reported surface wind conditions and the available landing directions must be considered. Before an airplane is type certified by the Federal Aviation Administration, FAA, it must be flight tested to meet certain requirements. Among these is a demonstration of being satisfactorily controllable with no exceptional degree of skill or alertness on the part of the pilot in 90-degree crosswinds up to a velocity equal to 0.2 VSO. This means a wind speed of 2/10 of the airplane's stalling speed with power off and landing gear flaps down. Regulations require that the demonstrated crosswind velocity be included on a placard in airplanes certificated after May 3, 1962. The headwind component and the crosswind component for a given situation can be determined by reference to a crosswind component chart. See Figure 8-19. It is imperative that pilots determine the maximum crosswind component of each airplane they fly and avoid operations in wind conditions that exceed the capability of the airplane. Common errors in the performance of crosswind approaches and landings are attempting to land in crosswinds that exceed the airplane's maximum demonstrated crosswind component, inadequate compensation for wind drift on the turn from base leg to final approach, resulting in undershooting or overshooting, inadequate compensation for wind drift on final approach, unstabilized approach, failure to compensate for increased drag during side slip, resulting in excessive sink rate and/or too low an airspeed, touchdown while drifting, excessive airspeed on touchdown, failure to apply appropriate flight control inputs during rollout, failure to maintain direction control on rollout, excessive braking. Turbulent air approach and landing. Power on approaches at an airspeed slightly above the normal approach speed should be used for landing in turbulent air. This provides for more positive control of the airplane when strong horizontal wind gusts or up and down drafts are experienced. Like other power on approaches, when the pilot can vary the amount of power, a coordinated combination of both pitch and power adjustments is usually required. As in most other landing approaches, the proper approach attitude and airspeed require a minimum roundout and should result in little or no floating during the landing. To maintain good control, the approach in turbulent air with gusty crosswind may require the use of partial wing flaps. With less than full flaps, the airplane will be in a higher pitch attitude. Thus, it will require less of a pitch change to establish the landing attitude, and the touchdown will be at a higher airspeed to ensure more positive control. The speed should not be so excessive that the airplane will float past the desired landing area. One procedure is to use the normal approach speed plus 1/2 of the wind gust factors. If the normal speed is 70 knots and the wind gusts increase 15 knots, airspeed of 77 knots is appropriate. In any case, the airspeed and the amount of flaps should be as the airplane manufacturer recommends. An adequate amount of power should be used to maintain the proper airspeed and descent path throughout the approach, and the throttle retarded to idling position only after the main wheels contact the landing surface. Care must be exercised in closing the throttle before the pilot is ready for touchdown. In this situation, the sudden or premature closing of the throttle may cause a sudden increase in the descent rate that could result in a hard landing. Landings from power approaches and turbulence should be such that the touchdown is made with the airplane in approximately level flight attitude. The pitch attitude at touchdown should be only enough to prevent the nose wheel from contacting the surface before the main wheels have touched the surface. After touchdown, the pilot should avoid the tendency to apply forward pressure on the yoke, as this may result in wheelbarrowing and possible loss of control. The airplane should be allowed to decelerate normally, assisted by careful use of wheel brakes. Heavy braking should be avoided until the wings are devoid of lift and the airplane's full weight is resting on the landing gear. End of Chapter 8, Part 3.